Hi everyone, I hope you're doing well. So in this video, we're going to discuss Leetcode problem of the day, and today's problem is longest increasing subsequence, and it is a medium level problem. Now this is a very standard problem, and this idea can be used in multiple other problems as well. I have personally seen this particular idea being used in other problems. Not exactly the longest increasing subsequence, but the idea that we are going to discuss just now. Right. So the problem is very straightforward. It says that we have been given a simple array. We have to figure out the length of the longest strictly increasing subsequence. So strictly means that, as you can see in this particular example, all the values are 7. They are increasing, but they are not strictly increasing, because after 7 I need a value greater than 7, right? And the length of the longest increasing subsequence in this particular case will be 1. Now let us discuss this particular example where we have 4. So what can be the longest increasing subsequence? We can see 0, 1 and then 2 and then 3, right? So subsequence is basically you can remove any number of elements from the given array and the remaining elements will be considered a subsequence, right? So again, this problem, let us discuss this particular test case as well. So they have given the example that in this particular example you can consider first 2. So this is of length 1, then 3, so length is 2, then 7, length is 3, and then 101, length is 4. Instead of 101, you could have also taken 18, because 18 is greater than 7. That would also have been correct, right? So how do we actually solve this particular problem? Very standard problem. So let me just write it first. We are going to solve this problem using DP, and the DP that is being used here is a very interesting DP. So we are going to use a one-dimensional DP. So let me just move it a little bit to the center. So now we have this one-dimensional DP. What is DP of I denoting? So DP of I is denoting the minimum last element of any subsequence of length n I, right? So this is what I was talking about, that when I say that this is an interesting DP, we generally don't use this kind of DP. This is very different when you study it for the first time. So DP of I here is going to denote the minimum last element of any subsequence of length I, right? Now you might ask, how is this information going to help us? Let's say now I have any value x, right? And I know DP of I. So let's say I have any value x and I know DP of I is less than x, right? So that means I can form a subsequence of length I plus 1 by inserting x. Let me just repeat this part again. So let's say DP of 2 is equals to 4. That means there exists a subsequence of length 2 which is ending with 4, right? Now my question was, how is this information helpful to me? Let's say now I have a value 5. So if I know that DP of 2 is equals to 4, then definitely I can form a subsequence of length 3 by adding 5 after this particular value. So let me just give you an example now. So let's say this is a subsequence, right? So if I change the values, if I write 4 here, so this is a subsequence of length 2 where I know the ending element is 4, right? Can I insert a 5 after it to make it a subsequence of length 3? Yes, that is definitely possible. So that is exactly what I am saying here, that if I know that there is a subsequence of length 2 which is ending with 4, then I can definitely insert 5 after it to make it a subsequence of length 3. So where did this 3 come from? It is basically this value plus 1, 2 plus 1, or in a general case I plus 1, right? So here I can write further now. If I know if DP of I is less than x, that means I can set DP of I plus 1 as minimum of DP of I plus 1 comma x, right? So you have to be very careful about this, that you will have to set minimum of both of the cases. Why? Because there could have been, let's say instead of 5, so let me erase this. Instead of 5 we had 6 here. So let me just write DP of 1, let's say, is equals to 1, DP of 2, let's say, is equals to 4, and DP of 3, let's say, is equals to 5 right now, and we encounter an element 6, right? So now I see that DP of 2 is smaller than 6, right? Now in this particular case, if I just directly replace if I directly replace the dp of I plus 1th position with 6, now this is going to violate my property which I stated here, right, which was the fundamental state of my dp, that I should denote the minimum last element of any subsequence of length I, right. But here earlier it was 5 and now I have replaced it with 6, which is not correct. If there was already a subsequence of length 3 which is ending with 5, then I should be putting 5 here, right. So this is the only reason we take dp here. So right, that is why we have taken minimum of both of the values. Now you can clearly see why is it like this. So how can we actually form the solution? So let me write it now. I'm just going to write a simple for loop. Let's say I have defined my dp. So vector int dp of size, let's say n, right. Here everything is 1 based. You can also take it 1 based or 0 based, it doesn't really matter. So let's say I'm taking it 0 based. So I'm going to initialize it with very big values, infinity, right. Now what will happen is, so let's take it 1 based only for easier understanding. So dp of 0 is now going to be 0, or let's say very small value, minus infinity, right. So now what I am saying is the dp of 0 is equals to minus infinity, that if you want to form a subsequence of length 0, then you can take any very small value. So why am I doing this? I am doing this to add the first element, right. So this one will only be added at the first index when the 0th index has some smaller value than this particular value, right. That is why I do this here. So now what I can do is, I can write a simple for loop for int I is equals to 0, I is less than n, I plus plus, right. So I am going to traverse through all the elements. So let's say my current value is nums of I, right. Now I am going to traverse through the dp array. Int j is equals to 0, j is less than n minus 1, let's say, and j plus plus, or n itself, right. So we are going till n minus 1th position. Now what I am going to do is, I am going to say if dp of I is less than my current value, then my dp of I plus 1 is going to be minimum of dp of I plus 1 comma current value, right. So this part is very simple to understand. What I am essentially doing is, I am taking one element in current value. Now I am making another for loop to traverse to the dp array, right. So in this particular dp array, what I am basically doing is, I am checking if my dp of I is less than my current value. That is exactly what I was checking here, that if my dp of 2 is less than my current value, right. In this particular case, if it is less than, I can try to replace the next position dp of I plus 1 by current value, right. And I will only replace it if it is smaller. That is why I am taking the minimum of both the values, right. So this is how you can solve this particular problem. The problem with this particular approach is, this is O of n square. I believe this should get passed in today's problem of the day, but let us just try to optimize this particular problem. I believe till now you were able to understand what is a dp state denoting, what is like why are we replacing these values with another value, and how are we actually trying to replace it. This solution is going to take O of n square time. That is why we are going to have a look at another optimized solution. Now if you carefully see at the definition and even this particular example as well, you will always realize that for the ith position we are storing the smallest element possible, right. For subsequence of length 1, then subsequence of length 2, we are trying to store the smallest position. Now what will happen in the final array or the final dp array? We observe that the final dp array will always appear in strictly increasing order, right, or increasing order in a sense. That means the dp array will always look sorted. So when the array always looks sorted, what can we apply? We can apply simple binary search. So instead of going through all the values like this and checking which element is smaller than my current value, I can apply binary search to find out the last position which is smaller than my current value, right. So basically, let's say this I had, let me just draw a dp array and then it will be easier to understand. So let's say now we have a dp array, right, and then we have some elements into it. So I am going to take some elements, let's say 10, then 20, then 30, then 40, then 50, then 60, and then 70. So basically this array is denoting that if I have a subsequence of length 1, the minimum element that a subsequence of length 1 can end with is 10. Then the minimum element that a subsequence of length 2 can end with is 20, and then 3, 4, 5, 6 and 7 and so on. Right. So these are all the values that I currently have. Now what can I try to do is, I say that I have a new value, let's say 45. Right. So I need, with the previous method, what I would have done is I would go here, then I say okay, so this value 10 is less than 45. So what I would do, at the next position I will take the minimum of 20, 45, which is 20 itself. Then I take the minimum here, then I take the minimum here, and at this particular position also 40 is less than 45. So what I would do is I will take the minimum of 50 and 45 at the 5th position. So now this 50 will get updated to 45, and then when I come at the 5th position, 45 will not be less than 45, and hence I know I cannot move any further, right? So this is what I could have done in the previous method, in n square method. But now since I know that these elements are already sorted, why do I need to search the whole array? I can simply apply binary search to find the value 45, right? So why am I only finding 45? So if I apply lower bound, let's say if I use the inbuilt C++ STL function lower bound, what it will give me? It will give me the position which contains 45 or any element greater than 45. In this particular case, it is going to give me the position of 50. So now if I apply lower bound, I can directly replace this element 50 with 45, right? And now I have updated my DP array. As simple as that. Instead of traversing through the whole DP array, I am just updating the simple value using lower bound. I am getting the position of the value. Now let's say again I get the element, let's say the next element is 60. So now what will happen if I apply lower bound? I will get the position of this particular element, and this is exactly what I wanted, right? Why? I'll tell you a reason why. So let's say if you wanted to have only an increasing sequence, there is no condition on strictly increasing, you just want an increasing sequence, right? So that means elements 60 and 60 are allowed like this, right? So in that particular case, you would want to look for some value greater than 60, right? Why? Because if you look, let's say you look for 61, so you will get at this particular position. Now if you replace this value with 60, then it is a valid case if it is a increasing sequence. But this is not possible here, since these two values cannot be the same. This sequence has to be strictly increasing. That is why we are only looking for the value 60. So I am telling you the reason why we are only looking for 60, not 60 plus 1, not 60 minus 1, anything other than that. We are only looking for the value 60 only. So now if I look for 60, I see that this particular position 60 is already present. Despite that, we are just going to take the minimum. So in our actual implementation, this is also going to update again by 60, right? So there was no change in the array, but our algorithm will update this particular value by the minimum of both the values, right? So this is how we can solve this problem. Instead of going through all the values, we observe that this particular array has increasing values, so why not directly apply binary search to find the correct position where I should insert the current element, right? So this is how you can solve this problem. Now let me show you the final code. And there is one more thing, like before showing the code, one more thing that I wanted to discuss. We have discussed what is the DP array, how to fill the DP array, but we did not discuss one simple part. How do we actually find the length of the longest increasing subsequence, right? So we discussed that initially all the values are initialized to infinity, right? So from the right, the first value which is not infinity is going to be the length of the longest increasing subsequence, that particular index. So let's say I traverse from right to left, this is infinity, so I ignore it. At this particular position, I encounter a value that is not infinity, so I do not take 70, but I will take the index 7, right? Because this actually denotes the length of the increasing subsequence. This denotes the smallest element that is ending in a subsequence of length I, right? So now we can have a look at the code. So what we have here is I have initialized the value n, which is the size of the nums array. Now I have initialized this dp vector, initialize all of them with infinity value. So as you can see, the values are up to only 10 to the power 4 here, so I can take 10 to the power 5 as infinity. Now I am finding the position of the current element nums of I, right? So I am just applying simple lower bound function. If p is less than n, that means if it lies inside the dp range, I am going to update dp of p as minimum of dp of p comma nums of I. Right. So here I have taken zero based indexing. I explained everything in one based indexing so that it is easier to understand. But here I have just taken zero based indexing. You can also take one based. It's totally up to you. Now what I have done here is, and also one more thing, if you take one based indexing, just make sure that dp of 0 is initialized to minus infinity, minus 1e5, right. So this is one thing that you will have to take care of, and also here you will have to change the for loops a little bit, and you will have to change this particular value, right. So a couple of changes. The most important one was this one, at dp of 0 should be minus 1e5 now, minus infinity, and you have to change the for loops and the return value here, right. Other than that, everything will be the same. So let me just keep it back here, right. So now after I have calculated the dp array, I'm just going to make a reverse for loop, and if at any position my I is less than 10 power 5, I'm going to return I plus 1, simply because I have taken 0 based indexing. So I have to return 1 based index value, right. So at the end I can return return 0. So this situation will never get triggered actually, but if you don't include this will give me compilation error, because this return statement is inside an if statement, and it recognizes that sometimes that if condition might not get triggered and this return statement will never get triggered, but we know that it is always going to get triggered. But to avoid compilation error, we just include this return 0 at the end, right. So let me just quickly submit this and show you. So as you can see, like I've attempted this problem a couple of times for now, like the latest one is accepted, the one just I just submitted. All the other ones also, you see that I've constantly improved my solution. So if I try to show you this particular solution, I believe this will be the one with the n square approach, right. So this is the one with the n square approach, and you can also solve this problem in this way. So that way will also be correct, right. So here I have taken a little bit different implementation. So as you can see, I have taken dp of I as maximum of dp of I comma dp of j plus 1. So this is a little bit of implementation. I don't want you to get confused, but I just wanted to show you that an n square approach will work, right. So you can ignore this particular implementation. It was just to show that n square will also work here. So the first like solution I showed will also work. So that is it for this particular video. I already guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to share thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you, and it will be able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.